Hello there, and welcome to Sleepy Science Vault. There is something pulling at the universe. Not violently, not suddenly, but with a slow, immense, and patient force, drawing entire galaxies, clusters, and superclusters across hundreds of millions of light years, all toward a single region of space. We call it the Great Attractor. And for decades, it was one of the most unsettling mysteries in all of modern astronomy, because we could feel its pull long before we could see what was causing it. The story begins with motion. Specifically, with motion that didn't make sense. When astronomers began carefully mapping the velocities of nearby galaxies in the latter half of the 20th century, they expected to find the kind of movement you'd predict from an expanding universe, galaxies drifting apart, carried outward on the flow of space-time itself. But that's not what they found. Instead, they found something stranger. Galaxies were moving in ways that didn't match the predictions. Their velocities were off. Not randomly off, but off in a specific direction, as if something, somewhere, was exerting a gravitational pull powerful enough to tug entire galactic systems off their expected paths. These are what astronomers call peculiar velocities. Not peculiar in a casual sense, but in the precise scientific sense of motion that cannot be explained by the expansion of the universe alone. Something else was responsible. Something was pulling. The Great Attractor was first inferred not by seeing it, but by noticing a mismatch, a disagreement between where galaxies appeared to be based on their redshift, and where their actual motion suggested they were going. That mismatch pointed like an arrow toward a region in the direction of the constellations Centaurus and Norma, a region dense, gravitationally significant, and at the time, almost completely hidden behind the plane of our own Milky Way. And here is what makes this truly remarkable. The Milky Way itself is moving toward it. Not just a few rogue galaxies on the outskirts of our neighborhood, but our entire galaxy, along with the local group, the Virgo cluster, and the vast Hydra Centaurus supercluster, are all streaming in the same direction, at roughly 600 kilometers per second. That is approximately 1.3 million miles per hour. A speed almost impossible to imagine. And yet, on the scale of the cosmos, it is the slow, steady drift of objects caught in something much larger than themselves. This streaming motion, this great collective flow, is one of the most striking large-scale features of the observable universe. It shows up even in the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. Astronomers measure a subtle asymmetry in that ancient light, a dipole pattern, and embedded within it is the signature of our motion, our inexorable drift toward the Great Attractor. Early discussions in cosmology were dominated by the question of why the local group was moving toward the Hydra Centaurus region at all. What was there? What could possibly be generating a gravitational influence on this scale? The answer, when it slowly came into focus, was both satisfying and humbling. The Great Attractor is not a single object. It is a region, an extraordinary concentration of mass, of galaxies, of dark matter, of cosmic structure, sprawling across tens of millions of light years, exerting its influence across an even vaster volume of space. And before you let your imagination run too far into the dramatic, the Great Attractor is not going to swallow us. The Milky Way will not be consumed. The pull is real, and the motion is real, but the universe is also still expanding, and on the very largest scales, that expansion will ultimately win. What the Great Attractor represents is not a doom, but a window. A window into how gravity operates not just between stars, or between galaxies, but between the largest structures the universe has ever built. Something is pulling at the cosmos. And for a long time, we barely even knew it was there. To understand the Great Attractor, you first have to understand something about the way astronomers measure the universe, and why, for a long time, those measurements kept returning answers that simply didn't add up. When we look at a distant galaxy, one of the most reliable tools we have is redshift. As the universe expands, light from distant objects is stretched, shifted toward the red end of the spectrum, and the amount of that shift tells us how far away the galaxy is, and how fast it's moving away from us. It is an elegant technique, and for most of the 20th century, it was the foundation of extragalactic astronomy. But redshift only tells part of the story. It captures the overall expansion of the universe, the smooth, predictable flow of space-time carrying everything apart. What it doesn't cleanly separate out is something else entirely, the peculiar velocity of a galaxy. The additional motion caused not by expansion, but by gravity. By the pull of matter on matter, structure on structure, across vast distances. And it is in those peculiar velocities, those small but meaningful deviations from the expected flow, that the first whispers of the Great Attractor began to emerge. The patterns astronomers eventually mapped were striking in their range. Galaxy velocities in the affected region differed from what expansion alone would predict by anywhere from positive 700 kilometers per second to negative 700 kilometers per second. Some galaxies were moving faster than expected. Some slower. But the deviations were not random, they were coherent, organized, pointing toward something. The first hints appeared as far back as 1973. Astronomers noticed anomalies in galactic motion that resisted easy explanation. By 1978, those anomalies had become harder to ignore. Reports of abnormal motion were quietly circulating through the astronomical community, a gathering sense that something in the large-scale structure of the universe was not behaving as the standard models predicted. The data was there. The signal was real. But pinning it down, identifying the source, mapping its influence, giving it a name and a location, that would take another 8 years. It wasn't until 1986 that the Great Attractor was formally identified. The discovery came from a remarkable collaboration, a group of 7 astronomers who would later become known, with a certain cinematic affection, as the 7 Samurai. Their names were Donald Lindenbell, Sandra Faber, David Burstein, Roger Davies, Alan Dressler, Roberto Turlovich, and Gary Wegner. Together, they undertook one of the most ambitious observational projects in cosmology at the time, a systematic study of elliptical galaxies spread across a vast region of the sky. They measured roughly 400 of them. 400 elliptical galaxies, carefully selected, painstakingly observed, their distances calculated through a technique that compared the intrinsic brightness and internal velocity of each galaxy to determine how far away it truly was, independent of redshift. This method, known as the Faber-Jackson relation, allowed the team to compare where a galaxy appeared to be based on its redshift, against where it actually seemed to be based on its physical properties. And the difference between those two measurements, that gap, revealed motion. Real, gravitationally driven motion, on a scale that no one had quite anticipated. What emerged from all of that careful, painstaking work was not a discovery made by looking at light in the traditional sense. There was no dramatic moment at the telescope where someone pointed at a glowing object and said, "There." The Great Attractor was not seen. It was inferred. It was reconstructed from the behavior of galaxies around it, the way a current in the ocean can be felt before it is seen, or the way a planet was first deduced from the wobble it caused in the motion of its star. This is one of the things that makes the Great Attractor so philosophically interesting. It was discovered through absence, through what was missing from the equations, through the motion that couldn't be accounted for any other way. Astronomy, at its most profound, is often the science of deduction, of reasoning carefully from what you can see to understand what you cannot. And what the Seven Samurai deduced was this: there was a region, centered roughly in the direction of the Centaurus and Norma constellations, at a distance of around 250 million light-years, where an extraordinary concentration of mass was quietly, persistently, reshaping the motion of everything around it. Not a single object. Not a star, or a black hole, or even a single galaxy. The Great Attractor is a region, a vast gravitational basin, a broad concentration of matter that sprawls across tens of millions of light-years. Think of it less like a drain and more like a gentle valley in the landscape of space-time, a place where the terrain of gravity slopes inward, and over billions of years, matter has been slowly, inevitably, flowing downhill. Within that region are galaxies. Clusters of galaxies. Enormous clouds of gas and dark matter. The Norma cluster sits near its heart, a dense, rich cluster of galaxies that represents one of the most significant concentrations of mass in our cosmic neighborhood. But even the Norma cluster is just one piece of a much larger, more diffuse structure that has no sharp edges, no clear boundary, no single point you could travel to and say, "This is it. This is the center." The Great Attractor is, in a sense, a place defined entirely by its influence rather than its appearance. And that influence, as those 400 elliptical galaxies quietly testified, is real, measurable, and vast. It took decades of observation, an ingenious measurement technique, and a group of 7 dedicated scientists to bring it into focus. And even then, what they had found was not a thing you could photograph or point a camera at, but a gravitational truth written into the motion of hundreds of galaxies across an enormous stretch of the cosmos. The universe had been hiding something enormous in plain sight. And in 1986, we finally began to understand what it was. There is a temptation, when we hear a name like the Great Attractor, to picture something. Something visible. Something dramatic, a vast luminous structure, perhaps, or a colossal black hole burning at the center of everything, reeling galaxies in like a cosmic whirlpool. The name almost demands an image. but the reality is quieter than that. And in its quietness, it is somehow more profound. The Great Attractor is not a star. It is not a nebula, glowing with ionized gas and captured light. It is not a black hole, at least not in any simple sense, and it is not a galaxy you could point a telescope toward and observe as a single coherent object. It is something harder to hold in the mind, and yet, in many ways, more representative of how the universe actually works at its largest scales. It is a region of intergalactic space. An expanse of the cosmos where matter, visible matter, dark matter, gas, galaxies, and the vast gravitational fields they generate, has accumulated over billions of years into a concentration significant enough to bend the motion of everything around it. Not a thing so much as a place. Not an object so much as a condition. When astronomers use the term Great Attractor, they are, in a precise sense, describing a gravitational effect more than a physical structure. It is a name for the pull, for the anomalous motion, the peculiar velocities, the large-scale streaming that drew scientific attention in the first place. The region producing that effect is real, and the mass within it is real, but there is no sharp boundary, no surface, no edge you could cross and say you had arrived. The Great Attractor is less like a mountain and more like the low point of a wide, shallow basin, something you understand best not by standing in it, but by watching how everything around it moves. This is, admittedly, a strange kind of discovery. We are accustomed to science revealing things, objects, particles, structures that can be cataloged and described in concrete terms. But some of the most important discoveries in cosmology are discoveries of behavior, of pattern, of the way the universe organizes itself on scales too large for any single image to capture. The Great Attractor belongs to that category. It was found in motion. It lives in motion. Its reality is expressed not in light, but in the slow gravitational choreography of thousands of galaxies drifting across hundreds of millions of light years. Modern cosmology has refined our understanding of it further still. Rather than treating the Great Attractor as an isolated anomaly, a single mysterious pull at one specific location, contemporary astronomers increasingly understand it as a node. A gravitational node embedded within a far larger network of cosmic structure. The universe, on its grandest scales, is not a smooth or uniform place. It is threaded with filaments of dark matter and gas, punctuated by dense clusters and superclusters of galaxies, and divided by enormous empty voids that stretch across hundreds of millions of light years. The Great Attractor sits within this web, a particularly significant concentration within an already complex landscape, one junction in a vast cosmic architecture that shapes the flow of matter across the entire observable universe. To understand it fully, you have to zoom out. You have to let go of the idea that the most important things in the cosmos are the ones you can see most clearly, and allow yourself to think at a scale where individual galaxies become almost incidental, data points in a larger pattern, leaves carried by a current far bigger than any one of them. And so, where exactly is this region? Where, in the vastness of the observable universe, does this gravitational basin lie? The answer depends slightly on who you ask and when they were writing, because measuring distances at cosmological scales is genuinely difficult, and estimates have been refined over the decades as our tools and techniques have improved. But the broad picture is this: the Great Attractor lies somewhere between approximately 150 and 250 million light-years from Earth. In the context of everyday distances, that number is simply beyond comprehension. A light-year alone, the distance light travels in a single year, moving at nearly 300,000 kilometers per second, is roughly 9.5 trillion kilometers. Multiply that by 200 million, and you begin to approach the scale we are discussing. And yet, in the context of the observable universe, which stretches roughly 46 billion light-years in every direction from where we stand, 250 million light-years is not so terribly far. The Great Attractor is, in cosmic terms, a neighbor. A distant neighbor, certainly, but within the same broad region of the universe that astronomers refer to as our local cosmic environment. The more classical estimates place it at roughly 65 megaparsecs from Earth. A megaparsec is a unit astronomers use when discussing truly large distances. 1 megaparsec is approximately 3.25 million light-years. 65 megaparsecs, then, works out to something in the range of 200 million light-years, comfortably within the broader distance range that more recent estimates have confirmed. The largest and most recent calculations lean toward the higher end of that range, placing the core of the Great Attractor's influence closer to 250 million light-years away. What makes pinning down this distance so challenging is precisely what makes the Great Attractor so unusual in the first place. Because it is not a single object with a well-defined position, there is no single point you are measuring the distance to. You are measuring the distance to a region, a diffuse, extended gravitational influence that has no precise center and no clear edge. Different measurements, using different galaxies and different techniques, will naturally return slightly different values depending on exactly which part of the region they are sampling and how the underlying mass is distributed. There is also the matter of the zone of avoidance, one of the great ironies of the Great Attractor's location. It sits almost directly behind the densest part of our own Milky Way's disk, from our perspective on Earth. All of that interstellar gas and dust that makes up the plane of our galaxy acts as an enormous curtain, blocking a significant portion of the electromagnetic spectrum and making it genuinely difficult to observe what lies beyond. For years, this meant that the very heart of the region we most wanted to study was hidden behind the galaxy we live in. Optical telescopes could barely penetrate it. The Great Attractor was frustratingly, almost deliberately, concealed. It was only with the advent of radio astronomy and X-ray observations, wavelengths that can pierce the dust where visible light cannot, that astronomers began to see through the zone of avoidance and get a clearer look at what was actually there. What they found confirmed and enriched the picture that the peculiar velocity data had already suggested: a genuine overdensity of galaxies and mass, centered in the Norma cluster region, embedded within a broader concentration of structure that extended across an enormous volume of space. The distance to that concentration, that gravitational basin sitting between 150 and 250 million light-years away, is not just an astronomical measurement. It is a reminder of the scale on which the universe conducts its affairs. We live on a planet, orbiting a star, inside a galaxy that is itself being gently, imperceptibly, but measurably drawn across the cosmos toward a region most of us have never heard of, at a speed that dwarfs anything in human experience. The Great Attractor is not close, but it is not unreachably remote either. It occupies a middle distance, significant enough to influence our motion, far enough that its full structure took decades of careful work to begin to understand. And the more carefully astronomers looked, the more they realized that the Great Attractor itself might only be part of the story. If you were to step outside on a clear night and look up at the southern sky, you might find the constellation Norma, a small, faint pattern of stars sitting in one of the richest parts of the Milky Way. It is not among the most celebrated constellations. It doesn't carry the mythology of Orion or the romance of Scorpius. It is modest, quiet, easily overlooked. Nearby sits Triangulum Australe, the southern triangle, similarly unassuming, a compact arrangement of 3 stars that most casual observers would pass over without a second thought. And yet, somewhere beyond those stars, far beyond them, at a distance so vast that the stars themselves are just foreground decoration, lies the heart of the Great Attractor. Hubble observations have helped refine its position to the border region between these two constellations, in a part of the sky that sits almost directly along the plane of our own galaxy. That detail, its position relative to the Milky Way, turns out to be one of the most significant and frustrating facts about the Great Attractor. Because the same region of sky that points toward one of the most gravitationally significant structures in our cosmic neighborhood is also the region most thoroughly obscured by our own galaxy's disk. But before we arrive at that obstruction, it is worth pausing to appreciate the sheer scale of the influence we are talking about. The Great Attractor does not exert its gravitational pull over a tidy, well-defined volume of space. Its influence extends across hundreds of millions of light-years, a reach so enormous that it affects the motion of galaxies not just in its immediate vicinity, but across a vast surrounding region that includes our own local group, the Virgo cluster, the Hydra Centaurus supercluster, and countless other structures spread across an almost incomprehensible expanse of the cosmos. This is not the gravity of a star holding planets in orbit, or even a galaxy holding its own stars together. This is gravity operating at the very largest scales the universe permits, the slow, patient, irresistible accumulation of mass across millions of light years, generating a gravitational landscape that shapes the long-term trajectory of everything within its reach. Galaxy motions across this entire region bear its signature. The streaming flows, the peculiar velocities, the subtle but consistent deviations from what pure cosmic expansion alone would predict, all of it reflects the underlying gravitational reality of the Great Attractor and the broader structure it anchors. When astronomers map the velocity field of galaxies in this part of the universe, they see a coherent pattern, a flow, like the movement of air around a region of low pressure, organized, consistent, and pointing in the same direction across an area of space that contains thousands upon thousands of individual galaxies. That is the scale of the influence. And it emanates from a direction that, for much of modern astronomy's history, we could barely see into at all. The reason is the Zone of Avoidance. It is a wonderfully evocative name, and an accurate one. The Zone of Avoidance is the region of sky that lies along the plane of the Milky Way, where the density of our own galaxy's stars, gas, and dust is so high that it becomes extraordinarily difficult to observe anything beyond. From our position inside the disk of the Milky Way, looking outward along the plane of the galaxy is like trying to see across a vast, dusty room with the lights off and a crowd of people standing in the way. The light from distant objects, galaxies, clusters, the structures we most want to study, is scattered, absorbed, and obscured before it can reach us cleanly. For optical astronomy, the zone of avoidance is essentially a wall. Visible light, which is what traditional telescopes detect, interacts strongly with interstellar dust. Each grain of dust scatters and absorbs photons, and when you are looking through the full thickness of the galactic disk, through thousands of light years of accumulated gas and dust and countless intervening stars, the cumulative effect is dramatic. Distant galaxies that would be perfectly visible in other parts of the sky simply disappear. Their light never makes it through. This is a profound irony in the story of the Great Attractor. The structure that has the most measurable influence on our galaxy's motion, the gravitational feature most responsible for the large-scale flow of matter in our cosmic neighborhood, happens to sit almost directly behind the densest part of our own galaxy from our point of view. The universe, it seems, placed its most interesting neighbor precisely where it would be hardest to see. For the early researchers who first inferred the Great Attractor's existence from peculiar velocities, this obscuration was a source of genuine scientific frustration. The data pointed clearly toward the Norma Triangulum Australe region. The motion of hundreds of galaxies testified to something massive and gravitationally dominant in that direction. But looking directly at it, seeing it, mapping it, understanding its detailed structure, was a problem that optical telescopes alone could not solve. The dust and stars of the Milky Way are not perfectly uniform in their obscuring effect, which means some windows exist, small patches within the zone of avoidance where the interstellar material is thinner, where a determined observer might glimpse something of what lies beyond. Astronomers have made creative use of these windows over the years, patiently searching for galaxies peeking through gaps in the obscuration. Some of the earliest direct observations of structure in the Great Attractor region came from exactly this kind of careful, painstaking work, finding the places where the curtain was thinnest, and looking through. But windows are not the same as clarity. Even the best optical observations through the zone of avoidance are compromised by reddening, the way dust preferentially scatters blue light, leaving everything shifted toward the red and making accurate measurements of brightness and distance significantly more difficult. The data you can extract is real, but it is imperfect, filtered through a medium that distorts and dims and complicates everything it touches. The solution, when it came, arrived from a different part of the electromagnetic spectrum altogether. Radio waves and X-rays behave very differently from visible light when they encounter interstellar dust. Radio wavelengths, in particular, pass through dust clouds with relatively little absorption. They are simply too long to interact strongly with individual dust grains, and so they travel through the galactic plane in a way that visible light cannot. X-ray observations, conducted from space-based telescopes operating above Earth's obscuring atmosphere, offer another avenue into regions that optical instruments cannot penetrate. Infrared observations, sitting between visible light and radio on the electromagnetic spectrum, provide yet another tool. Dust that blocks visible light is often transparent at longer infrared wavelengths, allowing a clearer view of the underlying structures. These complementary approaches, developed and refined from the 1980s onward, began to pull back the curtain on the zone of avoidance in a way that earlier generations of astronomers could only have dreamed of. And what they revealed in the direction of Norma and Triangulum Australe confirmed what the velocity data had long suggested: a genuine, substantial overdensity of galaxies in mass, concentrated in a region that had been hidden from easy view for so long precisely because of where we happened to be standing in the cosmos. The Norma cluster, catalogued as Able 3627, emerged from this process as one of the most significant individual structures in the Great Attractor region. Rich in galaxies, massive, and relatively nearby in cosmic terms, it sits close to the inferred center of the gravitational concentration. But even with the Norma cluster identified and studied, the full picture remained elusive. The broader structure of the Great Attractor, the diffuse, extended mass distribution that generates its far-reaching gravitational influence, continued to resist easy characterization, partly because so much of it remains behind the galactic plane, and partly because distinguishing individual components of such a large, irregular structure is genuinely difficult even with the best available instruments. Even today, parts of the Great Attractor region remain only partially understood. The zone of avoidance has not been fully conquered. There are portions of the sky in that direction that remain, in a very real sense, almost completely mysterious, regions where the obscuration is severe enough that even radio and infrared observations struggle to give a complete picture. The mass distribution, the precise boundaries of the gravitational influence, the detailed structure of what lies at and around its center, these remain active areas of research, questions that current and future generations of telescopes are still working to answer. There is something strangely fitting about that. The Great Attractor has been shaping the motion of our galaxy for billions of years, drawing us steadily across the cosmos at over 1,000,000 miles per hour, and yet it remains, in significant measure, hidden. Not hidden through any lack of effort or ingenuity on the part of the scientists who have dedicated careers to understanding it, but hidden by the simple, elegant, maddening fact of our own galaxy standing in the way. We live inside the Milky Way. We cannot step outside it. We cannot move to a better vantage point and look at the Great Attractor from a direction unobscured by our own home. We are, in the most literal sense, trapped inside our own galaxy's shadow, looking outward through its disk at a universe that is simultaneously revealed and concealed by the very structure we inhabit. The Great Attractor pulls at us from behind a veil. And the veil, after all these decades, has only partially lifted. Science, at its most persistent, is the practice of finding ways around obstacles. When the zone of avoidance stood between astronomers and the Great Attractor, the response was not to abandon the question. It was to look differently. To reach for tools that the obscuring dust could not stop, wavelengths of light that travel by different rules, that interact with matter in different ways, that carry information through regions where visible light simply cannot go. Infrared astronomy was one of the first such tools to be brought to bear on the problem. Infrared radiation occupies the part of the electromagnetic spectrum just beyond the red end of visible light, wavelengths too long for the human eye to detect, but well within the range of purpose-built detectors, both ground-based and space-based. And crucially, infrared light is far less affected by interstellar dust than visible wavelengths are. The dust grains that scatter and absorb optical photons so efficiently become largely transparent at longer infrared wavelengths. A galaxy that is completely invisible to an optical telescope peering through the galactic plane might still reveal itself clearly in the infrared, its stars still glowing, its structure still intact, its distance still measurable, even through the densest foreground obscuration. This property transformed the study of the zone of avoidance. Infrared sky surveys, particularly the large systematic surveys conducted from the late 20th century onward, began to reveal galaxies in regions of the sky that had previously appeared empty or impenetrable. The 2-micron all-sky survey, known as 2MASS, was among the most significant of these efforts, mapping the entire sky in 3 near-infrared wavelength bands and uncovering thousands of previously undetected or poorly characterized galaxies behind the galactic plane. In the direction of Norma and Triangulum Australe, these surveys began filling in the picture that optical observations alone had left frustratingly incomplete. Radio astronomy offered another avenue. Radio waves occupy the longest wavelengths in the electromagnetic spectrum used for astronomical observation, and they pass through interstellar dust almost entirely unimpeded. Surveys of neutral hydrogen, the most abundant element in the universe, which emits a characteristic radio signal at a wavelength of 21 centimeters, allowed astronomers to detect and measure the velocities of galaxies in the zone of avoidance without needing to see them optically at all. The hydrogen signal carries both the presence and the redshift of a galaxy encoded within it, and it travels through the galactic plane as freely as if the dust weren't there. For mapping the large-scale distribution and motion of galaxies in obscured regions, the 21-centimeter line became an invaluable tool. X-ray observations, conducted from space-based telescopes, contributed yet another layer of information. Hot gas in galaxy clusters emit strongly in X-rays, and X-ray photons at the relevant energies are not significantly absorbed by interstellar dust. Satellites such as Rosat and later XMM Newton and Chandra were able to detect galaxy clusters in the zone of avoidance through their X-ray emission, providing distance estimates and mass measurements for structures that remained invisible to ground-based optical telescopes. The Norma cluster itself was characterized in considerable detail through X-ray observations, confirming its status as one of the most massive clusters in our cosmic neighborhood. And then there are the deep optical searches, a more labor-intensive but remarkably effective approach that deserves its own acknowledgement. Even in the densest parts of the zone of avoidance, the obscuration is not perfectly uniform. The interstellar medium is clumpy and structured, and there are variations in extinction, the dimming of background objects, from one small patch of sky to the next. Patient, systematic optical searches can work through even heavy foreground extinction if the observations are deep enough and the analysis careful enough. By taking very long exposures, using sensitive modern detectors, and applying corrections for the known properties of the interstellar dust, astronomers have been able to identify galaxies even in some of the most obscured parts of the sky, tracing the large-scale structure of the Great Attractor region through the deepest layers of extinction that the galactic plane imposes. The combination of all these approaches, infrared surveys, radio observations, X-ray satellites, and deep optical searches, has produced a picture of the Great Attractor region that is richer and more detailed than anything the early discoverers could have assembled. It is still incomplete. There are still portions of the sky where the obscuration is severe enough to defeat even the most determined multi-wavelength campaigns. But the broad outlines are clear, the major structures are identified, and the gravitational landscape of the region is understood in a way it simply wasn't in the 1980s when the Great Attractor was first named. What that accumulated evidence has revealed, however, is a story more complicated than the original simple picture suggested. And a significant part of that complication has to do with mass, with the question of how much matter is actually concentrated in the Great Attractor region, and how confident we can be in any answer. The earliest estimates, made in the years immediately following the 1986 discovery, suggested a truly staggering concentration. The mass required to generate the observed streaming velocities, the coherent flow of galaxies at 600 kilometers per second across such an enormous volume, was initially put at something in the range of 10 to the 16th solar masses. Written out, that is a 10 followed by 16 zeros, a number so large it barely registers as meaningful to human intuition. For comparison, the Milky Way itself contains perhaps a few 100 billion solar masses of visible matter, and perhaps 1 trillion solar masses including dark matter. The Great Attractor, on those early estimates, would have to contain the equivalent of millions of Milky Way galaxies worth of mass to account for the gravitational influence it appeared to exert. Some subsequent estimates push the figure even higher, toward 10 to the 17th solar masses. These numbers seemed almost impossibly large. And as the field developed and the analysis was refined, it became clear that part of the apparent signal was not entirely what it seemed. One important complication was something called Malmquist bias, a subtle but consequential statistical effect that arises when you try to measure the distances and velocities of galaxies using flux-limited surveys. The problem is this: in any survey that detects galaxies above a certain brightness threshold, you will naturally tend to preferentially include the intrinsically brighter galaxies in your sample, because they are visible at greater distances. This means your sample is not a perfectly representative cross-section of the galaxy population, it is skewed toward the more luminous end. And when you use that biased sample to infer distances and then calculate peculiar velocities from the discrepancy between inferred and observed distances, the bias in the distance measurements can produce apparent streaming motions that are partly or wholly artifactual, signals of motion that are really signals of a systematic error in how the distances were measured. Malmquist bias was not an obscure technicality. It was a genuine concern that several researchers identified and worked to quantify in the years following the initial Great Attractor papers. When corrections were applied, some of the apparent amplitude of the streaming flow was reduced. Some of what had been interpreted as evidence for an extraordinarily massive concentration was revealed to be partly a product of the way the sample had been constructed and the distances had been estimated. This did not mean the Great Attractor was an illusion. The fundamental signal, the large-scale streaming motion, the coherent flow toward the normal region, remained real and robust after the corrections were applied. What changed was the estimated mass required to explain it. The corrected figures were still large by any ordinary standard, but they were more modest than the initial headlines had suggested, and they pointed toward a structure that, while genuinely significant, might not require quite such extreme concentrations of matter as the first estimates implied. Later studies added another layer of complexity, the recognition that much of the mass in the Great Attractor region, as in the rest of the universe, is likely unseen. Dark matter, the invisible, non-luminous component of matter that makes up the majority of the mass in galaxies and galaxy clusters, dominates the mass budget of any large-scale structure. The luminous matter we can detect, the galaxies and hot gas that reveal themselves across the electromagnetic spectrum, is only a fraction of the total. Any estimate of the Great Attractor's mass based on counting visible galaxies and clusters will necessarily undercount the true total, because the bulk of the mass is simply not emitting any radiation that our telescopes can detect. The distribution of dark matter in the Great Attractor region is not precisely known. Inferring it requires either gravitational lensing observations, which are difficult to conduct in obscured regions, or careful modeling of the observed velocity field, working backward from the motions of galaxies to reconstruct the underlying mass distribution that must be responsible. Both approaches have been pursued, with increasing sophistication as computational power and observational capabilities have grown. The results confirm that the total mass in the region is dominated by dark matter, as expected, and that the visible structures, the Norma cluster, the surrounding galaxy overdensity, are embedded within a much more extensive dark matter concentration that extends well beyond what any optical or radio survey can directly detect. So the search for the source, for the true nature and mass of what is pulling at us, has led to a picture that is simultaneously more detailed and more uncertain than the original discovery suggested. More detailed because we now have multi-wavelength maps, cluster identifications, velocity field models, and dark matter estimates that simply didn't exist in 1986. More uncertain because each new layer of investigation has revealed additional complexity, biases to correct for, unseen mass to account for, larger structures to consider. That makes the simple question of how much mass is there genuinely difficult to answer with precision. What we can say with confidence is that the Great Attractor region is real, massive, and gravitationally dominant over an enormous volume of space. The exact figure, whether it is closer to 10 to the 16th or 10 to the 17th solar masses, and how much of that is dark, remains an open question, one that different studies answer somewhat differently depending on their methods and assumptions. What we can also say is that the effort to answer that question has driven some of the most creative and ambitious observational work in modern cosmology. The necessity of seeing through the zone of avoidance pushed astronomers to develop and refine techniques that have since found applications far beyond the study of the Great Attractor alone. The effort to correct for Malmquist bias sharpened the statistical rigor of peculiar velocity studies across the field. The recognition that dark matter dominates the mass budget of large-scale structures, self-evident in retrospect, but not always fully appreciated in the early days, has informed how cosmologists think about structure formation across the entire universe. The Great Attractor, in this sense, has been more than a mystery. It has been a teacher. A problem demanding enough, and interesting enough, to drive the development of better tools and better thinking, and patient enough to keep revealing new layers of complexity long after its initial discovery. The search for its source is, in a meaningful way, still ongoing. For a while, the Great Attractor seemed almost too large to be real. The early mass estimates, those extraordinary figures suggesting concentrations of 10 to the 16th solar masses or more, implied something so dominant, so gravitationally overwhelming, that it almost strained credibility. And as observational techniques improved and more data came in from different directions and different wavelengths, a quieter but important revision began to take shape. X-ray surveys, in particular, told a more measured story. X-ray astronomy is especially well suited to measuring the mass of large-scale structures because hot gas, the intracluster medium that fills the space between galaxies and massive clusters, radiates strongly in X-rays, and the temperature and distribution of that gas encode information about the gravitational potential holding it in place. A more massive structure will have hotter, more extended gas emission. By modeling the X-ray brightness and temperature profiles of structures in the Great Attractor region, astronomers could make independent estimates of the mass present, estimates that didn't rely on the peculiar velocity techniques that had produced the original, larger figures. What the X-ray surveys found was sobering in a certain sense, though clarifying in another. One of the most significant of these efforts was the CISA survey, the Clusters in the Zone of Avoidance survey, specifically designed to identify and characterize galaxy clusters behind the galactic plane using X-ray data from the Rosat satellite. The CISA results, when they came in, suggested that the mass in the Great Attractor region was substantially lower than the original estimates had implied. Not just modestly lower, but roughly 1/10 of the initial figure. 1/10. That is a significant revision. It means the concentration that generates the observed streaming motions, while still genuinely massive by any reasonable standard, does not require the extraordinary accumulation of matter that early analyses had suggested. Some of that original signal, as we have already seen, was partly an artifact of Malmquist bias and the statistical challenges of early peculiar velocity work. The X-ray data added independent confirmation that the true mass was more modest, and in doing so, shifted the question somewhat. If the concentration is less extreme than first thought, then what exactly is producing the large-scale flow? And where does most of the gravitational influence actually reside? Part of the answer, as it turned out, lay in a structure that had been partially visible from early on, but whose true significance only came into full focus as the observations improved. The Norma cluster. Catalogued formally as Able 3627, the Norma cluster had been known as a significant galaxy cluster for some time before it was fully appreciated as the likely heart of the Great Attractor region. Its position in the Zone of Avoidance had made detailed study difficult, and for years it sat in the catalogue as an interesting but not fully characterized object, its properties somewhat uncertain, its precise mass and structure harder to pin down than those of clusters in more easily observed parts of the sky. It was X-ray observations that finally brought the Norma cluster into sharp focus. The hot intracluster gas of a massive cluster is an X-ray source of considerable luminosity, bright enough to be detected even through the obscuration of the galactic plane by space-based X-ray telescopes operating above Earth's atmosphere. When that gas emission was mapped in the Norma cluster's direction, what emerged was the clear signature of one of the most massive gravitational systems in our local cosmic neighborhood. Rich in galaxies, deeply embedded in an extensive dark matter halo, and positioned almost exactly where the theoretical predictions had suggested the gravitational center of the Great Attractor region ought to be, Able 3627 went from interesting footnote to central character in the story. Its location is remarkably precise in its alignment with theoretical expectations. The Great Attractor had been predicted to occupy a region of the sky in Norma and Triangulum Australe, at a distance that placed it within a specific range of recession velocities as measured by its redshift. The Norma cluster's velocity was measured at 4,844 kilometers per second, a figure that places it comfortably within the predicted distance range, consistent with the location of the gravitational center that peculiar velocity analyses had been pointing toward for years. It sits, in the language of cosmology, near the bottom of the gravitational potential well, the deepest point of the basin, the place where matter has most thoroughly accumulated, the location around which the broader structure is organized. The mass estimate for the Norma cluster itself is remarkable. Able 3627 has been estimated to contain approximately 5 times 10 to the 15th solar masses, that is, 5,000 trillion times the mass of our Sun, concentrated within a single gravitationally bound system. To put that in some kind of perspective, the Milky Way, including all of its dark matter halo, contains perhaps 1 trillion solar masses. The Norma cluster outweighs it by a factor of roughly 5,000. It is, by any measure, a vast accumulation of matter, a system so massive that it bends the motion of galaxies not just in its immediate vicinity, but across a region that extends for hundreds of millions of light-years in every direction. Later surveys, as they improved in sensitivity and coverage, confirmed and extended this picture. The Norma cluster emerged from these analyses not merely as one significant cluster among several in the region, but as the most massive known cluster in the entire Great Attractor area. Subsequent observations using both X-ray and radio techniques, combined with increasingly sophisticated optical and infrared surveys that penetrated ever deeper into the zone of avoidance, consistently pointed to Able 3627 as the dominant concentration of visible mass, the gravitational anchor around which the surrounding large-scale structure is organized. There is something deeply satisfying about this, from a scientific standpoint. The Great Attractor was first inferred as a theoretical necessity, a concentration of mass that had to exist somewhere to explain the observed motions of galaxies. For years, it was a name attached to an effect rather than an object, a label for something felt but not seen. And then, as the instruments improved and the obscuring veil of the galactic plane was gradually penetrated, there it was, not a featureless gravitational abstraction, but a real, identifiable, extraordinarily massive cluster of galaxies sitting almost exactly where the theory had predicted, at the bottom of the gravitational well that had been drawing our galaxy and everything around it for billions of years. The Norma cluster is not the entirety of the Great Attractor. The broader concentration of mass in the region extends well beyond any single cluster, diffused through the surrounding large-scale structure in the form of galaxy groups, filaments, and dark matter concentrations that do not resolve into any single identifiable object. But as the closest massive cluster in that region, as the structure sitting nearest to the predicted gravitational center, and as the most massive known cluster in the area. Able 3627 represents the best answer available to the question that has hung over this whole story from the beginning. What, exactly, is at the center of the pull? It is a cluster of galaxies. A magnificent, overwhelming, almost incomprehensibly massive cluster of galaxies, hidden behind our own galaxy, revealed only by the X-rays emitted from its superheated intergalactic gas, located at a distance of roughly 220 million light-years in the direction of Norma, and massive enough, in combination with the broader structure surrounding it, to have been gently, persistently redirecting the trajectory of the Milky Way for longer than the Earth has existed. The revision of the mass estimates, which initially seemed like a deflating development, a scaling back from something impossibly grand to something merely extraordinary, turns out to have been a clarification rather than a disappointment. The original inflated figures had implied a concentration so extreme that it sat uneasily with what was known about how structure forms in the universe. The revised picture, anchored by the Norma cluster and its measured mass of 5 × 10⁻⁵ solar masses, embedded within the broader but less extreme Great Attractor region, is actually more consistent with our understanding of large-scale structure formation. It is a concentration that fits, unusual and significant, but not physically implausible. A genuine feature of the cosmic landscape, rather than an anomaly that defied explanation. What the X-ray surveys gave us, in reducing the mass estimate by an order of magnitude, was not a smaller mystery. It was a more accurate one. And at the center of that more accurate mystery, revealed finally by the light that dust cannot stop, was Able 3627, the Norma cluster, sitting quietly at the gravitational heart of the Great Attractor, as it has been for billions of years, waiting to be found. The deeper astronomers looked into the Great Attractor region, the more they found that the story was not about a single object, or even a single cluster, but about something far more architecturally complex, a confluence of structures, a meeting point within the cosmic web where multiple large-scale features of the universe converge. The Norma cluster, for all its mass and significance, does not sit in isolation. It occupies a specific and meaningful position within the broader large-scale structure of the universe, at the intersection of the Centaurus wall and the Norma supercluster. These are not minor features. The Centaurus wall is a sheet-like concentration of galaxies extending across a vast region of the sky, one of the large-scale structures that defines the architecture of our cosmic neighborhood. The Norma supercluster is itself a significant overdensity, a collection of galaxy clusters and groups bound together on scales of tens of millions of light-years. And the Norma cluster sits where these two structures meet. This is not a coincidence. It is, in fact, exactly what you would expect from the physics of large-scale structure formation. In the cosmic web, matter accumulates preferentially at the intersections of filaments and walls, the places where multiple streams of infalling material converge. Over billions of years, those intersections develop into the densest nodes of the web, the richest clusters and superclusters, the gravitational anchors of entire regions of space. The Norma cluster's position at the confluence of the Centaurus wall and the Norma supercluster tells you something important about why it is so massive, and why the gravitational influence of the broader region extends so far. Some researchers have gone further, suggesting that it is precisely this confluence, the coming together of these two large-scale structures at a single gravitational focus, that is primarily responsible for the large-scale flow field we observe. The streaming motion of our galaxy and everything around it toward the Great Attractor region is not, in this view, the product of a single dominant concentration pulling everything toward it like a drain. It is the product of an extended, complex gravitational landscape shaped by the intersection of multiple large-scale structures, each contributing to the overall potential that drives the flow. The Great Attractor, in this framing, is less a destination than a convergence, a region where the architecture of the universe conspires to create an unusually deep gravitational basin. Within that region lies another structure that deserves particular attention, the normal wall. The normal wall is a large-scale concentration of galaxies, a sheet or wall of matter, in the language of large-scale structure, that extends across the surveyed region of the Great Attractor area. Like other great walls identified in the cosmic web, it represents a genuine overdensity of galaxies organized along a flattened, sheet-like geometry, the kind of structure that forms naturally as matter collapses along the filaments and intersections of the dark matter skeleton of the universe. The normal wall includes several named clusters and galaxy groups, distributed along its extent, each contributing to the overall mass and gravitational significance of the structure. The existence of the normal wall adds another layer of complexity to the Great Attractor picture. Rather than a roughly spherical concentration of mass centered on a single cluster, the region contains extended planar structures, walls and filaments, whose geometry affects how gravity operates across the surrounding volume. The streaming motions we observe in the surrounding galaxy population are shaped not just by the total mass in the region, but by how that mass is distributed, whether it is concentrated in a point-like cluster or spread across an extended wall or filament changes the detailed character of the gravitational field it generates, and therefore the detailed pattern of galaxy motions it produces. As surveys improved and coverage of the zone of avoidance became more complete, the picture that emerged from near-infrared and deep optical observations was subtler than many had hoped or expected. Rather than revealing a single new dominant cluster hidden behind the galactic plane, the kind of dramatic discovery that makes for a clean, satisfying headline, what the surveys found was something more diffuse. A smooth overdensity. A broad, extended concentration of galaxies spread across the region, without any single obvious new gravitational giant lurking in the obscuration. Near-infrared surveys, which were specifically designed to penetrate the zone of avoidance and reveal any major concentrations of mass hidden there, return this same result, a genuine overdensity of galaxies in the Great Attractor region, but no new major cluster of comparable significance to the Norma cluster. What had been hypothesized by some as a second great concentration, a hidden massive cluster deeper in the zone of avoidance that might account for the remaining discrepancy between the observed flow velocities and the mass visible in known structures, did not materialize. The overdensity was real, but it was smooth, extended, and distributed, rather than concentrated in a single dominant object. This finding was important in several respects. It confirmed that the mass in the Great Attractor region is genuinely more spread out than simple models had suggested, distributed across a complex network of clusters, walls, and filaments rather than concentrated in one or two dominant nodes. It meant that understanding the gravitational influence of the region requires modeling this extended, irregular mass distribution rather than simply placing a point mass at the center of a sphere. And it reinforced the view, increasingly prevalent in modern cosmology, that the Great Attractor cannot be fully understood in isolation. It must be studied as part of the broader cosmic web, as one node in a larger network of structures that shapes the gravitational landscape of an enormous volume of the universe. The cosmic web perspective has become the dominant framework for thinking about large-scale structure in modern cosmology, and the Great Attractor fits naturally within it. The universe, on its largest scales, is not a collection of isolated objects scattered through an otherwise featureless void. It is a network, a vast, intricate architecture of filaments, sheets, clusters, and voids, all interconnected, all responding to each other gravitationally, all part of a single coherent structure that formed from the tiny quantum fluctuations present in the early universe and grew, over 13 billion years, into the cosmic web we observe today. The Great Attractor region is one of the denser nodes of that web in our cosmic neighborhood, not an isolated anomaly, but an integral feature of the universe's large-scale architecture. And then, from an entirely different direction of investigation, came a discovery that illustrated just how much the Zone of Avoidance had been concealing from view, not in terms of massive clusters and dramatic concentrations, but in terms of something more quietly astonishing: individual galaxies, hiding in plain sight, invisible to conventional telescopes for decades. Blind hydrogen surveys, observations that scan the sky systematically in the radio emission of neutral hydrogen without targeting any previously known sources, began to uncover them. Galaxy after galaxy, detected through the 21-centimeter radio signal of their hydrogen gas, emerging from behind the galactic plane into the awareness of astronomy for the first time. Not because they were particularly faint or distant, but simply because the dust of the Milky Way had been hiding them from optical view, and no one had yet looked for them specifically in radio wavelengths across those regions of the sky. The word blind in this context is precise and meaningful. A blind survey makes no prior assumptions about where galaxies should or should not be. It simply listens, scanning systematically, accumulating data, detecting signals wherever they arise. And in the Zone of Avoidance, the signals arose with a frequency that surprised even those conducting the surveys. There were galaxies there. Not just a few, many. Galaxies of various sizes, at various distances, some in the immediate foreground, some at distances placing them within or behind the Great Attractor region itself. Galaxies that had been entirely absent from every optical catalog, unknown to astronomy, invisible to every instrument that relied on wavelengths that dust could stop. Their discovery was a humbling reminder of how incomplete our picture of the universe can be, even in our own cosmic backyard. For all the sophistication of modern astronomy, for all the advances in detector technology and survey strategy and data analysis, there remained, right in the part of the sky that had been most intensively studied for other reasons, an entire population of galaxies that we simply didn't know existed. The blind hydrogen surveys didn't just add entries to a catalog. They changed the way astronomers think about the mass and structure of the Zone of Avoidance. Each newly discovered galaxy contributes to the gravitational accounting of the region, adds to the total mass, influences the modeled velocity field, shifts the picture of what is actually there behind the galactic plane. Some of the newly detected galaxies turned out to be members of groups or structures in the Great Attractor region, adding to the census of matter in a region whose mass budget had always been uncertain precisely because so much of it was hidden. The story of the Great Attractor, in this sense, is also a story about the limits of knowledge, and about the creative, persistent, multifaceted effort to push past those limits. Every new wavelength explored, every new survey conducted, every previously hidden galaxy detected, adds another piece to a puzzle that has been growing more detailed and more nuanced for 4 decades. The picture that has emerged is not simpler than the original one. It is richer, more complex, more genuinely representative of how the universe actually works on its largest scales. A confluence of walls and superclusters. A smooth, extended overdensity rather than a single hidden giant. A population of previously unknown galaxies emerging from behind the curtain of the Milky Way. And threading through all of it, the gravitational signal that started everything, the streaming motion, the peculiar velocities, the unmistakable pull that drew scientific attention to this region in the first place, and has kept it at the frontier of cosmological research ever since. In 2016, a single radio astronomy study quietly rewrote part of the map of our cosmic neighborhood. The survey used the Parkes Radio Telescope in Australia, a large, sensitive dish antenna capable of detecting the faint 21-centimeter hydrogen emission from galaxies at considerable distances, to conduct a systematic scan of the zone of avoidance in the direction of the Great Attractor region. It was the kind of painstaking, methodical observational work that doesn't always generate headlines but forms the backbone of how science actually advances. Long hours of telescope time, careful data reduction, patient sifting of signals from noise, and the slow accumulation of a catalog that simply didn't exist before. When the results were published, they contained a number that stopped many astronomers in their tracks. 883 galaxies. In a region of sky that had been, for most of observational astronomy's history, effectively blank, obscured, avoided, treated as a zone where meaningful observation was impossible, a single radio survey had found 883 previously uncatalogued galaxies. Not all of them were at the distance of the Great Attractor. Some were foreground objects, galaxies in the relatively nearby universe that happen to lie behind the galactic plane from our perspective. But a significant portion were at distances consistent with the Great Attractor region itself, adding substantially to the census of matter in an area whose total mass had always been uncertain. The sheer number is worth sitting with for a moment. 883 galaxies. Each one a system containing billions of stars, potentially trillions of planets, vast clouds of gas and dust, enormous dark matter halos extending far beyond their visible edges. Each one a structure comparable in scale to our own Milky Way, or larger. And every single one of them had been, until that survey, simply absent from our maps, not because they didn't exist, not because they were too distant or too faint, but because the dust of our own galaxy had been standing in the way, and we hadn't yet looked for them in the right wavelengths with sufficient sensitivity. The 2016 survey did more than count galaxies. It began to organize them into structures, tracing the large-scale architecture of the region in a way that previous, patchier observations had not been able to achieve. Among the most significant findings were the identifications of several previously unrecognized or poorly characterized concentrations within the surveyed area. 3 of these were designated NW1, NW2, and NW3, new wall structures, or wall-like concentrations of galaxies, identified in the data for the first time. The naming convention is deliberately modest. These are not grand mythological titles, but functional designations that simply acknowledge the sequence of discovery. NW1, NW2, and NW3 represent distinct overdensities within the survey region, concentrations of galaxies that cluster together in position and velocity space in ways that suggest they are genuine physical associations, real structures in the cosmic web, not chance alignments. The same survey also identified CW1 and CW2, concentrations associated with the Centaurus Wall, the large-scale sheet of galaxies that we already knew passed through the Great Attractor region. These new identifications helped fill in the picture of the Centaurus Wall's structure and extent, adding detail to a feature of the cosmic web that had been known in broad outline but remained poorly characterized in the obscured portions of its length. And then there was a finding that, in its spatial scale, was perhaps the most striking of all. One of the structures identified in the survey appeared to be part of a filament, a thread of the cosmic web, that stretched approximately 180 degrees across the sky. Half the entire celestial sphere. A filament so extended in projection that it spans the full width of the observable sky from our vantage point, a continuous thread of enhanced galaxy density running from one horizon to the other when viewed in the relevant velocity slice. A filament of that projected extent is a remarkable thing to map. Filaments are the great highways of the cosmic web, elongated concentrations of dark matter in galaxies that connect clusters and superclusters, channeling the flow of matter between the denser nodes of the network. They can extend for hundreds of millions of light-years in physical space, and when one happens to be oriented roughly along our line of sight, or when we happen to be positioned near one in the cosmic web, it can appear to stretch across enormous arcs of the sky. The filament identified in the 2016 survey, if its apparent extent across 180 degrees reflects a genuine physical structure, would be among the larger coherent features identified in our cosmic neighborhood, another element of the complex architectural landscape within which the Great Attractor is embedded. What the 2016 study represented, taken as a whole, was a demonstration of how much the zone of avoidance had been suppressing our understanding of the universe in our immediate cosmic vicinity. The 883 galaxies, the new wall structures, the Centaurus wall concentrations, the extended filament, all of it was there, all along, waiting to be detected by instruments sensitive to the right wavelengths. The universe had not changed. Our ability to perceive it had. This is one of the recurring themes in the history of astronomy, and the Great Attractor region has illustrated it with particular clarity. The universe does not reveal itself all at once. It yields its structure gradually, incrementally, in proportion to the ingenuity and persistence of the instruments and methods brought to bear on it. Each new wavelength explored, each new survey conducted with greater sensitivity or wider coverage, each new analytical technique applied to existing data, has the potential to reveal structures in populations that were genuinely invisible before, not metaphorically invisible, but physically undetectable by any previously available means. The Great Attractor region, precisely because it sits behind the Zone of Avoidance, has been a particularly rich site for these kinds of revelations. Every improvement in our ability to see through or around the galactic plane has produced new discoveries there, new galaxies, new clusters, new structural features, new contributions to the gravitational accounting of a region that has been shaping our cosmic trajectory for billions of years. And yet, even as these discoveries accumulated, the Great Attractor itself was being progressively recontextualized within a larger framework, one that would, in time, suggest that the Great Attractor was not the final answer to the question of what is pulling at us, but rather the center of something even more vast. The Great Attractor, it turns out, is not merely a significant concentration in an otherwise ordinary region of the universe. It is, according to the best current understanding, the gravitational focus of one of the largest structures ever identified in the observable cosmos. That structure is called Laniakea. Laniakea is a supercluster of galaxies, the largest gravitationally coherent structure that our galaxy can be said to belong to. Its name comes from the Hawaiian words for immeasurable heaven, a poetic choice that reflects both the scale of the structure and the tradition of Hawaiian astronomy that has long guided observation from the mountains of the Pacific. It was formally defined and named in 2014, in a landmark paper that used peculiar velocity data, the same kind of galaxy motion analysis that had first revealed the Great Attractor, to map the boundaries of the gravitational basin within which our galaxy and its neighbors reside. The concept of Laniakea emerged from a recognition that the question of which supercluster our galaxy belongs to had never been satisfactorily answered. Superclusters are notoriously difficult to define. Unlike galaxies or galaxy clusters, which are gravitationally bound systems, objects that will remain together indefinitely, resisting the expansion of the universe, superclusters, in the traditional sense, are not bound. They are transient overdensities that will eventually be pulled apart by cosmic expansion. Defining their boundaries has always been somewhat arbitrary, a matter of convention rather than physics. The approach taken by the Laniakea paper was different. Rather than defining superclusters by their overdensity of galaxies alone, the researchers mapped the velocity flow field of the local universe, the pattern of galaxy motions extending across hundreds of millions of light years, and identified the boundaries not by galaxy counts but by the flow of matter itself. The idea was elegant. Within a supercluster, matter flows inward, toward the gravitational basin. At the boundary, the flow reverses, and matter begins moving toward a different basin. The boundary of a supercluster, in this framework, is a watershed, a dividing line between gravitational catchment areas, analogous to the ridgeline that separates river drainage basins on Earth. When this watershed analysis was applied to the local velocity field, what emerged was a structure of extraordinary scale. Laniakea spans approximately 500 million light-years in its longest dimension. It contains the mass equivalent of roughly 100 million billion suns, an almost unworkable number, representing a significant fraction of all the matter within the observable universe's local region. It encompasses the Milky Way, the Local Group, the Virgo Cluster, the Hydra Centaurus supercluster, the Perseus-Pisces supercluster, and hundreds of thousands of other galaxies spread across a volume of space that dwarfs any previously defined supercluster. And at the center of all of it, at the bottom of the gravitational basin that defines Laniakea's watershed, the point toward which all the matter within this vast structure is slowly flowing, is the Great Attractor. The Great Attractor, which began as an unexplained anomaly in galaxy velocities, which was then identified as a significant concentration of mass in the direction of Norma, which was progressively refined into a picture of the Norma cluster embedded within a complex network of walls and filaments. That same Great Attractor is now understood to be the gravitational heart of a supercluster containing hundreds of thousands of galaxies and spanning 500 million light-years. This is a remarkable conceptual journey. What was first perceived as a local puzzle, why are the galaxies near us moving in an unexpected direction, turned out, upon investigation, to be a window into the largest scale structure of the universe. The anomalous motions that first drew scientific attention to the Great Attractor region were not a local curiosity. They were the expression, at our scale and our location, of a gravitational landscape organized on a scale of hundreds of millions of light-years. The flow toward the Great Attractor is not just the motion of our galaxy toward a nearby concentration. It is the motion of everything within Laniakea toward the gravitational focus of the entire supercluster. We are, in other words, not just near the Great Attractor. We live within its gravitational domain, within the vast supercluster that it anchors, and have been drifting toward it, along with hundreds of thousands of other galaxies, since long before the Earth existed. The name Laniakea, immeasurable heaven, feels appropriate in a way that goes beyond poetry. It is a structure that genuinely resists easy measurement, that challenges our instruments and our intuitions, that requires new frameworks and new analytical approaches to even begin to characterize. And at its heart, drawing everything within it on a slow, billion-year drift, sits the structure that astronomers first noticed as a mismatch in galaxy velocities, a number that didn't quite add up, a pull that had no obvious explanation. The Great Attractor is not just an interesting anomaly in our cosmic neighborhood. It is the center of our supercluster home. There is a particular kind of discovery in science that doesn't close a question but instead opens a larger one, that answers one mystery by revealing the existence of a deeper mystery behind it. The Great Attractor, it turns out, is one of those discoveries. We have established that the Great Attractor is the gravitational focus of Laniakea, that the entire supercluster, spanning 500 million light-years and containing hundreds of thousands of galaxies, flows inward toward this region in the direction of Norma. That is already a picture of almost incomprehensible scale. But it is not the end of the story. Because the Great Attractor itself is moving. Not in the sense that all objects move, carried along by the expansion of the universe, drifting with the general flow of space-time. The Great Attractor is moving in the additional sense, the peculiar velocity sense, the same sense in which its gravitational influence was first detected. It has its own motion beyond what cosmic expansion alone would produce. And that motion points towards something even further away, even more massive, even less discussed in the popular understanding of cosmology. It points toward the Shapley supercluster. The Shapley supercluster, also called the Shapley concentration, lies at a distance of roughly 600 to 700 million light-years from Earth, in the same general direction as the Great Attractor but considerably further away. It is one of the most massive concentrations of matter in the observable universe, a supercluster of superclusters containing dozens of rich galaxy clusters and an estimated total mass that surpasses even the extraordinary scale of Laniakea. Named after the American astronomer Harlow Shapley, who first noted the region's unusual richness in galaxies in the 1930s, it represents a gravitational presence of truly exceptional magnitude, a concentration so large that its influence extends across hundreds of millions of light-years in every direction. And toward it, the Great Attractor is flowing. This means that the gravitational hierarchy extends further than the Laniakea picture alone suggests. The Great Attractor draws Laniakea toward it. But the Shapley supercluster draws the Great Attractor, and through it, everything within Laniakea, including our own galaxy, toward a destination even further along the cosmic chain. We are not just moving toward the Great Attractor. We are moving toward the Great Attractor, which is itself moving toward Shapley, in a nested sequence of gravitational influences that operates across increasingly vast scales. This means that the Great Attractor may not be the final destination. It is a gravitational focus, a real and significant concentration of mass, but it sits within a larger flow, a broader current in the cosmic river that ultimately leads toward the Shapley concentration. Whether it is meaningful to speak of a final destination at all is a question worth pausing on, because the universe is not a simple system with one attracting center and one eventual resting point. It is a web of gravitational influences, each structure pulling on its neighbors, each region both attracting and being attracted, in a complex dynamical system that has been evolving since the Big Bang and will continue evolving for billions of years to come. The early studies that first identified the Great Attractor were naturally focused on the most immediate, most detectable gravitational influence, the pull from the Hydra-Centaurus region that the peculiar velocities of nearby galaxies most directly reflected. The connection to Hydra-Centaurus was one of the first structural associations made, as astronomers tried to identify the specific concentrations of matter responsible for the observed streaming. The Great Attractor was, in those early discussions, often described in terms of its relationship to the Hydra-Centaurus supercluster, the large-scale structure in which the Norma cluster and the surrounding concentration are embedded. But as the observational reach extended and the velocity field was mapped across greater distances, the Shapley supercluster began to emerge as an additional contributor to the overall gravitational picture. The question became, how much of the observed flow toward the Great Attractor region is actually generated by the Shapley supercluster pulling from further away? How much of what we attribute to the Great Attractor is really Shapley's influence, operating at longer range? The answers, when researchers worked to disentangle the two contributions, were illuminating and somewhat humbling. Some analyses suggested that the Shapley supercluster accounts for only about 10% of the observed pull, that the Great Attractor region itself, and the broader Laniakea basin, are responsible for the dominant portion of the streaming motion we observe in our cosmic neighborhood. Shapley contributes, but it is not the primary driver at our scale and distance. The Great Attractor, and the confluence of structures that constitute it, genuinely dominates the local velocity field. But 10% of an already enormous gravitational signal is itself a substantial contribution. And the fact that Shapley's influence is measurable at all, that its gravitational fingerprint extends across 600 million or more light-years to affect the motions of galaxies in our part of the universe, speaks to the extraordinary scale on which the Shapley concentration operates. A structure whose gravitational reach extends that far, even at a fractional contribution, is a remarkable thing. And it sits in the same general direction as the Great Attractor, adding its pull to an already powerful current that has been redirecting our galaxy's trajectory for billions of years. There are researchers who argue that even Shapley does not represent the final word, that beyond Shapley, and beyond the Great Attractor, there are additional concentrations in voids whose gravitational influence contributes to the large-scale flow of matter across our region of the universe. The cosmic web is not a system with a single attractor and a single void. It has many nodes and many basins, each influencing the others, producing a velocity field of considerable complexity that no single attractor can fully explain. The Great Attractor, Shapley, and the other large-scale structures in our cosmic neighborhood are all part of this web, all contributing to and shaped by the gravitational landscape that defines the dynamics of our corner of the observable universe. What this means, in practical terms, is that the question of where we are ultimately going, which gravitational basin we in the Milky Way will eventually settle into, over timescales of billions or tens of billions of years, does not have a simple answer. The expanding universe complicates everything. As cosmic expansion accelerates, driven by dark energy, the more distant concentrations will eventually recede beyond the reach of their own gravitational influence. What can affect our galaxy's motion today may not be able to do so in the far future, as the universe continues to grow and the distances between structures increase. The Great Attractor's pull is real, but it may not ultimately dominate our galaxy's fate on the longest timescales. These are questions at the frontier of cosmology, questions that require combining observations of the velocity field with models of dark energy, the expansion rate, and the long-term evolution of large-scale structure. They do not have settled answers, and they may not for some time. What they have is the quality of all good scientific questions, genuine depth, real stakes, and the potential to teach us something important about the fundamental nature of the universe. And amid all these vast structural considerations, superclusters and their motions, gravitational basins nested within gravitational basins, flows that extend across hundreds of millions of light-years, there is a single image that brings the story of the Great Attractor back to something more immediate, more visual, more intimate in scale. A Hubble Space Telescope image of the region near the heart of the Great Attractor, in the direction of the Norma cluster, in the depths of the Zone of Avoidance, captured by peering through gaps in the galactic obscuration, contains, among its many galaxies, one that stands out in a particular way. It is a galaxy called ESO 137-002, and it is notable for being the largest visible galaxy in that field of view. But what makes ESO 137-002 truly remarkable is not what you can see in ordinary light. It is what you can only see in X-rays. ESO 137-002 has a tail. Not a tail of stars, not a stream of visible matter trailing behind it like a comet, but a tail of X-ray emitting gas, superheated plasma, stripped from the galaxy by the pressure of the surrounding intracluster medium as the galaxy moves through the hot gas filling the Norma cluster. This process, called ram pressure stripping, occurs when a galaxy moves through a cluster at high speed, and the intergalactic gas it encounters acts like a wind, pushing the galaxy's own gas back behind it in a long, glowing stream. The X-ray tail of ESO 137-002 is invisible to optical telescopes. It does not appear in ordinary photographs of the region. Only in X-ray images, taken by space-based observatories sensitive to the high-energy emission of superheated plasma, does the tail reveal itself, a ghostly streamer of gas extending behind the galaxy, silent testimony to the extraordinary violence of its passage through the dense environment at the heart of the Great Attractor. There is something deeply evocative about this image, and about what it represents. Here is a galaxy, one among hundreds of thousands in the Laniakea supercluster, being physically transformed by its environment at the center of the Great Attractor region. Its gas is being stripped away by forces it cannot resist, leaving a trail behind it that is invisible to ordinary light but glows in X-rays like a river of fire. It is a small-scale expression of the same fundamental truth that the entire Great Attractor story embodies, that gravity, operating at every scale from the motion of gas within a single galaxy to the streaming of entire superclusters across the cosmos, shapes the universe in ways that are simultaneously beautiful and merciless. ESO 137-002 will not keep its gas forever. Ram pressure stripping will eventually deplete the reservoir of star-forming material in the galaxy's disk, suppressing new star formation and slowly transforming the galaxy from a star-building system into a quieter, older, more quiescent one. The Norma cluster environment is doing to this galaxy, over hundreds of millions of years, what any sufficiently dense and hot environment does to galaxies that pass through it, stripping, transforming, reshaping. And the Milky Way is drifting toward this same region, slowly, imperceptibly on any human timescale, but measurably, inexorably, drawn by the same gravitational basin that has been organizing the motion of matter in our cosmic neighborhood since long before the first stars lit up in the early universe. We are part of this story. Not observers of it from a safe distance, but participants in it, carried along by forces operating on scales so vast that the entire span of human civilization is less than a single heartbeat in the timescale over which these motions unfold. The Great Attractor is not just out there, somewhere in the direction of Norma, a curiosity of modern astronomy. It is the gravitational center of our supercluster home. It is the focus toward which our galaxy has been drifting for billions of years. It is a region of the cosmos where hidden galaxies have been emerging from behind a curtain of dust, where X-ray tails trace the violence of galactic passage through hot intergalactic gas, where the entire architecture of a 500 million light-year structure converges on a single gravitational basin. And beyond it, further still, the Shapley supercluster pulls at everything, at the Great Attractor, at Laniakea, at our galaxy and every galaxy within our cosmic neighborhood, and a chain of gravitational influences that extends across scales where the distances themselves become almost philosophical in their magnitude. The universe is in motion. It has always been in motion. And the motion is not random, it is structured, organized, shaped by the architecture of the cosmic web into flows and currents and great rivers of matter that tell the story of how the universe has evolved from the smooth, hot, almost featureless state of the early cosmos into the intricate, hierarchical, endlessly varied structure we observe today. Somewhere in the direction of two quiet, easily overlooked constellations in the southern sky, behind the dust and stars of our own galaxy, at the heart of a supercluster whose name means immeasurable heaven, the Great Attractor waits. It has been pulling at us for longer than we can truly imagine. And it will be pulling at us, quietly, patiently, for longer still. Every structure in the universe has a lifespan. Not in the biological sense, galaxy clusters do not age and die the way living things do. But they evolve. They change. The gravitational relationships between them shift over time as the universe expands, as dark energy drives the large-scale geometry of the cosmos toward increasing isolation, and as the flows and currents that define the dynamic landscape of the present universe gradually lose their coherence. What is gravitationally significant today will not necessarily remain so forever. And the Great Attractor, for all its present dominance over the motion of matter in our cosmic neighborhood, is no exception to this rule. Current estimates suggest that the Great Attractor may remain an important gravitational influence for only a few more billion years, a figure that sounds vast by human standards, but is relatively modest on cosmological timescales. The reason is dark energy. The accelerating expansion of the universe, driven by this mysterious component that makes up roughly 68% of the total energy content of the cosmos, is steadily increasing the distances between large-scale structures. Gravitational influence falls off with distance. The further apart two concentrations of mass become, the weaker the pull between them. As the universe continues to expand and accelerate, the Great Attractor's reach will gradually diminish, and the coherent large-scale flow that currently draws hundreds of thousands of galaxies toward it will slowly dissolve into the expanding background. This is a profound thought to hold quietly. The streaming motion that has been shaping our galaxy's trajectory for billions of years, the gravitational current that drew scientific attention to this region in the first place, the flow that defines the boundaries of Laniakea itself, all of it is a feature of a particular epoch in the universe's history. We happen to live in that epoch. We happen to exist at a time when the Great Attractor is still a coherent, dominant gravitational influence, when Laniakea is still a meaningful structure, when the velocity field of the local universe still carries the clear signature of these large-scale flows. In the far future, the universe will be a quieter, more isolated place, where the cosmic web has been stretched and diluted by expansion to the point where the dramatic large-scale structures we observe today are shadows of what they once were. But that future is billions of years away. For now, the Great Attractor is very much present and very much real, and the structures within and around it continue to reveal new detail with each observational advance. Among the structures that have helped sharpen our understanding of the Great Attractor region is a cluster designated the Centaurus Crux cluster, a galaxy cluster identified in surveys of the region with a measured recession velocity of 6,214 kilometers per second. That velocity figure is not simply a number attached to a distant object. It is a distance indicator, a positional marker in the redshift space map of the local universe, placing the Centaurus Crux cluster at a specific location within the broader architectural landscape of the Great Attractor region and its surroundings. Its identification helped fill in the picture of how matter is distributed across the volume of space that the Great Attractor influences, adding another data point to the growing census of structures that collectively define the gravitational landscape of this part of the cosmic web. And at the heart of that landscape, consistently and repeatedly confirmed by every observational approach that has been brought to bear on the region, sits Able 3627, the Norma cluster, in a position so precisely aligned with theoretical predictions that it has become the anchor point around which all subsequent discussions of the Great Attractor are organized. Its velocity, measured at 4,844 kilometers per second, places it at a distance consistent with the predicted location of the gravitational center. Its mass, approximately 5 times 10 to the 15th solar masses, 5,000 trillion times the mass of our Sun, makes it the most massive known cluster in the region, a designation that has been confirmed and reconfirmed by successive surveys using different techniques and different wavelengths. It sits near the bottom of the gravitational potential well, the deepest point of the basin, the location toward which matter in the surrounding volume is most strongly drawn. These numbers, the velocity, the mass, the position, are not just entries in a catalog. They are the concrete, measurable expression of the abstract gravitational reality that the Great Attractor represents. When astronomers say that the Great Attractor is pulling our galaxy at over 1 million miles per hour, it is the mass of the Norma cluster and the structures surrounding it, mapped through these careful measurements, confirmed through these painstaking surveys, that underlies that statement. The numbers give substance to the concept. They transform the Great Attractor from a theoretical necessity into a physical reality with specific, quantifiable properties. The broader context of the Norma cluster's position adds another layer of significance to its role as the gravitational anchor of the region. It does not sit at a random point in the cosmic web. It occupies a specific architectural position, at the junction of two giant structures, where the Centaurus wall and the Norma supercluster converge. This junction is not incidental to the cluster's mass and dominance. It is, in a very real sense, the reason for them. In the cosmic web, junctions are special places. They are the points where the web's structural elements, its filaments and walls, intersect, where the matter flowing along multiple pathways through the web converges at a single location. Over billions of years, this convergence of flows produces the densest, most massive concentrations in the universe, the rich clusters and superclusters that sit at the nodes of the cosmic network. The Norma cluster is a product of exactly this process. The Centaurus wall and the Norma supercluster have been channeling matter toward this junction for billions of years, and the result is a cluster of 5 times 10 to the 15th solar masses, sitting at the bottom of the gravitational well of the Great Attractor, drawing everything within hundreds of millions of light-years toward itself. Several research teams, approaching the problem from different directions and using different datasets, have reached the same conclusion about the flow field in this region. It is the confluence of these two giant structures, the Centaurus wall and the Norma supercluster meeting at the position of the Norma cluster, that is primarily responsible for the gravitational basin we call the Great Attractor. Not a single dominant mass, not a mysterious hidden concentration, but the combined gravitational influence of two large-scale structures meeting at a single point, producing a flow field whose coherence and strength reflects the architecture of the cosmic web at this particular location. This understanding, refined over decades of observation and analysis, represents the mature scientific picture of the Great Attractor, a picture very different from the dramatic, slightly mysterious impression that the name itself might suggest. There is no single hidden giant, no mysterious object lurking behind the zone of avoidance waiting to be revealed, no source of gravity that defies the known physics of the universe. What there is something simultaneously more mundane and more wonderful, the natural consequence of the cosmic web's architecture, the inevitable product of two large-scale structures intersecting at a point that happens to lie in our cosmic neighborhood, producing a gravitational basin deep enough and extensive enough to organize the motion of matter across an almost incomprehensible volume of space. The Great Attractor is, in this sense, a feature of the universe's ordinary operation at extraordinary scales. It is what happens when the cosmic web produces a particularly significant junction in our local region of space. It is normal cosmic structure, just larger, more influential, and more consequential for our galaxy's trajectory than most. And yet, knowing all of this, knowing the mechanisms, knowing the mass estimates, knowing the structures responsible, knowing the role of the Centaurus wall and the Norma supercluster converging at Abel 3627, does not entirely diminish the sense of awe that the Great Attractor inspires. Understanding does not always dissolve wonder. Sometimes it deepens it. The fact that the universe, operating through the ordinary physics of gravity and large-scale structure formation, has produced a concentration massive and extensive enough to draw our galaxy across the cosmos at over 1,000,000 miles per hour, that this is simply what happens when two large-scale structures happen to meet in our neighborhood, is not a deflating discovery. It is an astonishing one. It means that the Great Attractor is not a freak occurrence, not an anomaly that requires special explanation, but a natural product of the same processes that have been shaping the universe since shortly after the Big Bang. It means that our galaxy's extraordinary journey toward a concentration of 5,000 trillion solar masses embedded in a supercluster spanning 500 million light-years is, by the universe's standards, entirely ordinary. There are likely many great attractors, many junctions in the cosmic web, across the vast expanse of the observable universe, where large-scale structures converge to produce gravitational basins of comparable or greater depth than the one our galaxy is drifting toward. We cannot observe most of them directly. The observable universe has limits, and the most distant concentrations are too far away for current instruments to characterize in detail. But the physics that produces the Great Attractor operates everywhere in the universe. The cosmic web is not unique to our neighborhood. Every region of the cosmos has its own architecture, its own nodes and filaments and walls, its own gravitational landscape that organizes the motion of matter across vast scales. We happen to live in a region that is one of the better studied examples of a particularly significant junction. We happen to be close enough to the Norma cluster and the confluence of the Centaurus wall and the Norma supercluster to feel their combined gravitational influence as a measurable streaming motion. We happen to exist at a time in the universe's history when these structures are still coherent, still exerting their influence, still organizing the large-scale flow of matter in our cosmic neighborhood. And we happen to have developed, over the course of a few decades of increasingly sophisticated observation and analysis, the tools and the understanding to recognize what this influence is, where it comes from, and what it tells us about the architecture of the universe we inhabit. The Norma cluster sits at the heart of all of this, measured, characterized, repeatedly confirmed as the dominant concentration in the region, its velocity and mass and position all consistent with its role as the gravitational anchor of the Great Attractor. The Centaurus Crux cluster adds its contribution to the surrounding structure. The confluence of the two great walls generates the flow field that has been shaping the motion of our galaxy for longer than the sun has been burning. And for a few more billion years, before dark energy stretches the distances too far, before the coherent large-scale flows dissolve into the expanding background, before the universe enters the quieter, more isolated epoch that awaits it in the far future, the Great Attractor will continue to do what it has always done. It will pull. Quietly, patiently, across hundreds of millions of light years, it will pull. And our galaxy will continue its long, slow journey toward the gravitational heart of the immeasurable heaven we call home.